Hi guys, friendly neighborhood calculus teacher here. Well, I guess not really here with you. Believe me, I would much rather be here with you than at home. I am recovering from some knee surgery and thought maybe this would be nice to make a video of today's lesson. That way our sub, Miss Richards, didn't have to worry about teaching calculus. Miss Richards will absolutely do everything she can to help you, I know. I just didn't want to have her worry about teaching you calculus because, hey, that's okay, that's my job. So if you would, go get your notes all ready. We are going to go start a new chapter, which is chapter 5. You can see it's all about maximums and minimums and things like that. And this is kind of where the chapter where we get to use all those derivatives that we were using last chapter. So last chapter we learned our chain rule and our product rule and our quotient rule and all those derivatives of inverse trig functions. Now we get to use them in more real life type situations. And it won't seem that way in the beginning of the chapter, but we definitely move that way in this chapter. So let's go get ready for chapter 5. Got your notes all ready? Got your calculator ready too? Go get your calculator ready because you're going to need it. I think I have mine over on the side. Anyway, so here we go. So just a kind of background information about why are we doing this. It says a useful thing we can learn from a derivative is derivatives will help you figure out maximums and minimums. Remember where that derivative is 0. And figuring out where these maximums and minimums are located. And we use those in some more everyday real life situations. We really do. Things like, how should I price this tractor to give us the maximum profit? I mean, those are things that John Deere and Case and all that figure out. If you price your tractor too high, then of course nobody's going to buy it. If you price it too low, then you're not going to make a good enough profit. You need to kind of get that happy medium where you still sell enough and it's not priced out of people's reach, and you make a good profit on each one that you sell. What speed should I drive to get the best gas mileage? A little different from every car, but that's actually a calculus equation. What's the least amount of plastic that I need to make this iPhone cover? So if you are the person manufacturing those iPhone covers, of course you want to use the least amount of plastic, so you have to buy the least amount of plastic, and then that helps your profit. Now, not everything has to do with profit. I mean, that second one is speed, but profit is kind of a big deal, and maybe you don't think about that, but that's actually some calculus. Okay, so we're kind of just going back and thinking about maximums and minimums, and if I have my graph of y equals x squared, you know that this graph really goes on forever. I don't have the arrows at the top of this parabola, but you know that this parabola does extend upwards forever. And it says, if I am using the interval -2 to +2, do you notice it has brackets here? So this is not a point, this is an interval. We're going from x equals -2 to x equals +2, brackets. So it's including those numbers, right? What's the absolute maximum value and what's the absolute minimum value? So I'm going to go look at my graph and figure out what in the world am I talking about here. I'm starting at x is -2. My graph is counting by 2's, just in case you're wondering, in case you can't see that. So at -2, I'm up here, and I'm including that, and I'm taking this part of my parabola all the way over here up until x is +2. And I put the dots so I know that I've started and stopped including at -2 and +2. Okay, so not too hard of a question, I don't think. What is your absolute maximum value? And so they want to know what's your absolute maximum y value. Well, what is our absolute maximum y value? All the way up at 4. And you don't have to write y equals 4. When you talk about absolutes, maximums, and minimums, we know we're talking y values. It's understood, so I promise it's okay just to write 4. So do we have an absolute minimum here? Yeah, we have a place where it dips down and it goes no further, and that would be here at 0. We have a y value of 0. So I do have an absolute maximum value. Actually, I have 2, but they're even, and I have an absolute minimum value. Okay, let's go start over. What happens if I can get my pen straight, what happens if I have a slightly different interval? So look at the next interval. It goes from 0 up until positive 2. The 0 has a parentheses, which means it's not including it. So I'm going from 0, I'm putting an open circle there, up until positive 2, x equals positive 2. So I'm looking at just this part of my parabola. Well, I still have an absolute maximum value. I still have an absolute maximum at y equals 4. And what about an absolute minimum? Well, at first thought, you'd think, okay, so my minimum is at y equals 0. But the problem is you have an open circle there. You don't actually have a value. You get really, really close to it, but you don't actually touch it. So we say there is none. Now you don't want to write 0, meaning none, because that means that you actually have a value of 0, a minimum value of 0. So you either put a blank, well, don't leave it blank, then it looks like you didn't answer it. I mean, put a slash or write none. Maybe it would be best for us to write none. There is no minimum value. There's not a dot, there's not a point, I can't name it, so we say there is none. Let's just look at a few more. Oops. So why don't you guys take just a second or two, read these over, pause the video for just a second and see if you can answer, and then check your answers with mine. And just in case you can't read, because I know how this is, you're still looking for absolute maximum and absolute minimum, and it says we are using the interval 0 to 2, 0 is included, 2 is not, and we're using negative infinity to infinity. Okay, so pause video and then check answers with me. You paused, right? Okay. So hopefully you have unpaused your video now, and let's go get ready to check answers. So I'm going from 0 to 2. 0 is included, 2 is not. I'm looking at just this part of my parabola, and I'm asking absolute maximum. Maximum, highest that I can on this interval. Well, I have a high point, but it's not really a point, it's an open circle, so I can't name it, so I say there is none. And what about an absolute minimum? I do have that. I have a point, it's filled in and everything, and that's y equals 0. Going from negative infinity to infinity, that's my entire graph. So go forget about that little open circle, the entire graph. What's my absolute maximum? Way the heck up there. Well, you kind of have one of two answers here. I don't really have a point, so I can say that it's infinity, or you can say that you really don't have one. Both answers really are okay. Technically, we'd probably say we don't have one because we can't stop it and we can't name it. But if you wrote infinity, I understand that because you did go all the way up. That's okay. So I'm going to go ahead and say none, but I understand the infinity answer. You aren't wrong. What about absolute minimum? We do have that, and that's y equals 0. So hopefully you did pretty okay on that. Nothing crazy, nothing you haven't had before. Now, why are we doing this? So what is this big idea? The whole big idea is that your domain plays a big role in figuring out your maximums and minimums. If you noticed on that last slide, when you changed your domain, when you changed your interval, what x could be, then sometimes you had a maximum, sometimes you didn't. Sometimes you had a minimum, sometimes you didn't. It depends on which part of the graph that you're looking at. So domain plays a big part on there. Just reminding you of some vocabulary words, you can have local maximums and absolute maximums. You remember the difference in those, right? You can have local minimums or absolute minimums. And the locals you can also call relative. You can call them a relative maximum or a relative minimum. Still lows or highs, just not the highest or lowest overall. So we're going to look for some local and absolute extrema. If you need to, go throw that word back in your notes, extrema. I hope you remember that extrema is just a kind of very general overall word that means a maximum or a minimum. Sometimes we'll ask you for an extrema because we don't want to give you a clue that, oh yeah, you're looking for a maximum or you're looking for a minimum. And sometimes it truly is just a shortcut instead of writing maximums and or minimums, just to say extrema. By the way, extrema is plural. If you have one, you have an extreme. If you have more than one, then you have extrema. We don't really say extremes, although you'll probably hear that some places, but really the mathematical way to say is extrema. So just be aware of that name. All right, so now that we get to talk about extreme, we have extreme value theorem. Please grab your notes and go write this one down. The extreme value theorem. First of all, you have to have a little background information on when you can use extreme value theorem. Your function has to be continuous, so no breaks, no holes, no asymptotes, nothing like that. And it has to be on a closed interval, which means it has to have a beginning point and an ending point. We can't start out with open circles or end with open circles. So you have to have something that is continuous, whether it's a line or a curve, and you have to have a starting and a stopping point. And then we're going to look for extremes, extrema. We're going to look for maxims and minimums. And the theorem says if it's continuous and it's closed, then you will have a maximum and a minimum value all the time. Now, you can have more than one maximum, you can have more than one minimum. Sometimes they're even, that's okay. But a minimum and a maximum exist. We don't say what they are, and we don't even say how many. We just say they exist. So I threw a few examples up here just so you can see sort of some differences in graphs. So the first one is just a straight line, as you can tell. I chose a positive slope, but it doesn't have to be. But it is continuous, and it is a closed interval. You have a starting point and a stopping point. And you can see on there you do have a maximum value. That would be over here at this endpoint at B. And you have a minimum, or a minimum point, and that's over here at A. Now, does that always mean it's, B is the maximum and A is the minimum? No, but I want to show you that there is a maximum and there is a minimum. Okay, so what happens if your graph is a little curvier? So second one is literally a curve, and I just threw a curve on there. Do you have a maximum? Sure. Well, it's not at A and it's not at B, the endpoints, but a maximum exists, and it would be somewhere around here. And a minimum exists, it would be somewhere here. It's on the graph itself. We say it's on the interior of our graph. It's on the graph. Okay? So what if it looks like this? Kind of a half circle, still a curve. Do I have a maximum? Yeah, I do. It would be kind of at the top of the curve, whatever y value that is, I don't know. And do I have a minimum? Yeah. I tried to draw really carefully, but my idea to try to show you was I actually have two minimums. I have a minimum at A and I have a minimum at B. They're supposed to be even. I think when I drew them, one's a little off than the other, but just pretend. So I have two minimums. They're even with each other, and that's okay. I've got minimums. And those happen to be at endpoints. So sometimes maxims and minimums are on the endpoints, and sometimes they're on the interior. But they exist, is all I'm trying to get you to see. And the last one, I don't know what it looks like. Maybe it's a Nike swoosh sign, maybe it's a fish hook or a candy cane, I don't know. Maximum, yep, got a maximum, got a minimum. So no matter what, if it has to be closed interval and it has to be continuous, no breaks, that there is a maximum and there is a minimum. Sometimes more than one, that's important. Sometimes there's more than one, like here's more than one minimum, but a minimum and a maximum exist. Now we'll go use this theorem and go find it, or find them. Okay, so if you were in class, I'd give you guys the pen and you guys would probably sit there and not come up and want to volunteer. Then somebody would break the ice. So just pretend. We've got our graph over here, and let's just go pretend and make sure we remember about where to find local maximums and where to find absolute maximums and things like that. So I am grabbing this absolute maximum, oops, and you can tell me, because I can hear you through here, right? You can tell me where this absolute maximum goes. Well, you know that it's a maximum. It's going to go with the very highest y value that we have, absolute highest. So on that same vein, I think I'll go ahead and get my absolute minimum. Lowest point on here. Are you thinking in your head where I should put this? hope it was right there. Okay, so let's go look at the other ones. A local maximum and a local minimum. Local maximum, I can have here, you can call it a relative maximum as well. It is a high point. It's just not the highest ever. That's okay. Another local maximum, it's okay if it's an endpoint. That's all right. It's still a high point. And I have a local minimum over here. All right. So just a thought. As you already know this, because I hope you're not rolling your eyes too much, look at this question down here. What do you know about the derivative at these extrema? What do you know about the derivative at these maximum and minimum points? So think about that tangent line that would kind of skim by. And what about the derivative at each one of these? I can hear you think this, right? Every time that derivative is 0. So that's probably something good to pause and go write down. And it's true. If you're going to have an extrema, the derivative is going to be 0. Sort of. That's our very next idea. So let me flip the side and you can write this down, right? Okay. So notice we got a blinky star. Okay, it's not blinking, it's twirling, but you get the idea. You really, really do need to write this down. So let me talk for a second and then you pause and make sure you have this written down. Since we're finding extrema, maximums and or minimums, every extrema, whether it's a maximum or a minimum, occurs at something called a critical point. It is a critical point in the life of this function. They always occur at critical points. Now, how do you find critical points? 3 ways. You got to test all 3. Critical points occur when the derivative is 0, which we already looked at. Could also be when the derivative is undefined, and the endpoints. You got to make sure you underline endpoints. That's the one everybody seems to forget. So let me do that one again. All extrema occur at critical points or endpoints. And a critical point is defined as when your derivative is 0 or when your derivative does not exist, when it's undefined. So if we go look for extrema, we have to look for 3 things. We have to find critical points, derivative is 0, derivative is undefined, and we have to look for endpoints. Since endpoints are something that people tend to forget, I usually take care of that first. That way I don't forget it. Okay, so what is she talking about? Let me see if I can make this a little better before we actually throw you into a problem. Okay, so I sketched a little curve, a little graph on here. Good thing I don't have to write the equation of it, okay? Just looking at this curve and how this goes, where do you have a derivative that is 0? Now I know that I drew it by hand. Just go with what you think I'm drawing here, right? Take it with a grain of salt. Where is our derivative equaling 0? Can you already tell? Of course you can. So, derivative is 0. I'm thinking it's supposed to be at b. That's supposed to be like the minimum part of a curve here. So I'm going to say it's going to be at b. What about at c? Well, that's not 0. That comes to a point. Remember, no derivatives at corners and cusps and things like that. D, that would have a derivative of 0. And I'm also going with E. That would have a derivative of 0. Tangent line, 0 slope, right? All right. So what about this question over here? Where is the derivative not existing? Remember, we don't have derivatives at corners and cusps, vertical tangents, and any kind of discontinuity. No discontinuities on this thing. Maybe I have some vertical tangents. I have a feeling I'm looking more for things like corners and cusps. So that would be A and C, right? I think I've got all my letters on there. So, oh, and I don't have any endpoints, right? No endpoints. I see I have an arrow and I have an arrow. Okay, so there's no endpoints to consider. If I look at all the places that have a derivative of 0 and a derivative that does not exist, this is the list that I would look at and go, if I have minimums and maximums, it comes from this list. Now, that doesn't mean that every one of these will be a maximum or be a minimum. We're just trying to narrow it down. Out of the bazillion points on a function, I have narrowed it down to 5 places, and from this list of 5, maximums and minimums come from here. So really we're just trying to narrow the list down, and then we'll test these 5. So from these 5, do you have maximums and minimums from this list? I think so. Let's go check out these questions. Okay, so of all of these points on here, which one or ones of these are relative maximums? Do you have an absolute maximum? Oh, there's minimums. Okay, so here's a relative maximum and a relative minimum. Well, maybe I'm going to go look at my other ones. I think I'm going to get my absolutes out of the way first. What do you think? So if I'm looking for absolute maximums and absolute minimums, if you're checking your graph for absolute maximums, did it actually come from this list? I think so. I think it's E. I think E looks a little higher up than A does. So I'm going to absolute maximum, is an E. And what do you know? It's from this list. What's your absolute minimum? It's got to be B. And what do you know? It comes from this list, right? What about that relative maximum that I was kind of looking for before? C is a relative maximum. What about relative minimums? I think I've got D. Well, let's see. Oh, I just need an A on here, right? A is a relative maximum. All right. So I think I have all of my maxims and minimums, and they came from these points. Okay. Now, I know I told you that not everything's going to be, but I guess I'm talking about absolutes. So if you have this list of 5, not every one of these is going to be an absolute maximum or an absolute minimum, but it is going to come from this list. Now let's throw you into a problem and you can see kind of what I'm talking about. Okay, let's go get this one written down, right? So we are going to find our absolute maximum and minimum. So sometimes we'll say just find the extrema, right? Of y equals f of x equals x to the 2/3 power. And we're going to look on the interval from -2 to +3 in brackets. No calculators. This would be a no calculator question. I know we could probably graph it and look at those values and figure it out, but we're going to do this without the calculator. And I'm also guessing that this is a graph that you probably don't know off the top of your head. Just a guess. Okay, so I wrote down here in steps, just in case. Step 1 is we've got to go find those critical points. We're figuring out where our derivative is 0, where our derivative is undefined, and we can't forget the endpoints. So I'm going to make this list. Hopefully it's not a very long list. And then our maximum and minimum will come from that list. We're just trying to narrow it down. Okay, so the first thing I do is go take care of endpoints, because I tend to forget endpoints. I don't want to forget endpoints. Do you have endpoints on this graph? Sure. It says that we're starting at -2 and ending at 3. That's our interval. That's our domain. So I know my critical points, I'm definitely going to have -2 as a critical point, and I'm going to have 3 as a critical point. So I've already got some out of the way. Let's go find the derivative, and then we'll figure out where the derivative is 0 and where the derivative is undefined. Now I've got to go find a derivative. So what do you think about finding the derivative of that function? That's that power rule. That's falling boxes, so fall down the 2/3. And then the 2/3 has to drop down by 1. What's 2/3 minus 1? -1/3. Okay. This is okay, and it is the right answer, but I'm going to rewrite it a little bit because I think that will help me figure out actually where the derivative is undefined and where the derivative is 0. Take that x to the -1/3, put it in your denominator. Now, whether you write it as a cube root or whether you write it as a 1/3 power, I don't think that matters, but make sure you put it in the denominator. So I have a 2 in the numerator and the 3 in the denominator, and I have x to the 1/3 power. Still good? If you wrote cube root, it's fine. That's okay. So, looking at this derivative, think about, first of all, where would this derivative be undefined? Well, it's undefined when your denominator equals 0. So I'm going to go do that. Where does that denominator equal 0? You can probably do that in your head, but if you need to, we can solve it out. We can divide by 3. And I guess we can, take it to the third power. Something to the 1/3 power is 0. I hope you know that that is 0. So that's another critical point. That's what makes my derivative undefined. It made the denominator equal 0. Now, if you're trying to figure out what makes your derivative equal 0, that's when your numerator is 0. Because you could have 0 over 1, or 0 over 2, or 0 over -6, 0 over whatever. That makes it 0. Look at your numerator. Is that thing going to equal 0? It doesn't have an x in it. There's no variable. It just has 2, so it's never going to equal 0. So then I don't have to worry about it. I do have a value that makes the denominator equal 0, but I don't have a value that makes my numerator equal 0. So I end up with 3 critical points. Okay, so that means in the life of this graph on this interval from what, -2 to +3, in the life of this graph, whatever it looks like, there are 3 possible places I have that could be the maximum or the minimum. 3's not bad. Okay, I can't always tell you're going to have 3, but generally I can say you're not going to have more than 4 or 5. That 5 is actually kind of a lot. Okay, so we have our critical points of -2 and 3 and 0. Now we're going to go check the y values. Okay, how do you find the y value? Put it back in the equation. So let's go put it back in the equation. Okay. So I'm going to take -2 and put it back in the equation, and that will test my y value. So I'm putting -2 into my function. -2 to the 2/3 power. Okay, I have no idea what -2 to the 2/3 power is, so I'm going to go check my handy dandy calculator. Give me a second to go grab my calculator. All right, so -2 to the 2/3 power. Give or take, I am using AP Calculus rules of 3 decimal places, 1.587. Good for you. So that's the y value. Okay, let's go try 3. At 3, if I put 3 into 2/3 power, again, I have no idea what 3 to the 2/3 power is. If you can do that off the top of your head, good for you. I'm getting 2.080. Since there's 0 after it, it is okay to call it 0.08. If you really need to, go put an extra 0, 3 decimal places, we're good. 0 to the 2/3 power, well, what's 0 to any power? Still 0. Okay, so what this is telling you is now these are your y values. These tell you how high up and how low down your function is. This says at -2, it went up, give or take 1.5. At -2, it went up about 1.5. Yeah, I'm guessing here, right? At 3, it went up just a hair more than 2. And at 0, we had a y value of 0. Now, I don't know for sure that this is exactly what my graph looks like. Here, here, here. I don't think it looks like a V. But of all of the points on this graph, in this interval, my maximum and minimum come from here. So which one is your minimum value? Right here, the lowest y value. Where's your maximum? The highest y value, right here. Now then you just have to be very careful about what the question says. If it asks for find the points, then we need to write them as points. Then we say that we have an absolute minimum at 0, 0. If it just says what's the value, then we want the 0. I'm going to kill this fly. Okay, so it says find the absolute maximum and minimum values. Then all I need are the 0 and the 2.08. There's my minimum values. Just be careful if it asks for a point. Let's try it again. Okay, so this is pretty much all we're doing here except one slight twist at the end. Hopefully you're just starting to see how this goes. Find the absolute maximum and the minimum of this function. 2x squared minus 8x minus 9. And we are on the interval from -1 to +4. Okay, so just take a second in your head and think, where do I find these extreme values? Critical points and endpoints. So I'm looking for where does the denominator equal 0, where does the derivative, where is it undefined? That's the denominator being 0. Where is the derivative equaling 0? That's the numerator part equaling 0. And my endpoints. So I'm going to go write endpoints down now so I don't forget them. I know I keep stressing that, but honestly, I truly remember doing this in school, and I remember being so concerned about getting my derivative right that I completely missed my endpoints every time. I can tell you, way back a bazillion years ago in high school, this was one of my worst sections because I never ever remembered the stupid endpoints, and I don't want you to make that mistake too. Okay, so critical points, for sure a -1 and a 4. Got them? Good. Let's go take a derivative. So our derivative, falling boxes, 4x minus 8. Well, that's pretty simple. Okay, so let's go think about where that derivative would equal 0. Well, where would that equal 0? Add 8, divide by 4. I'm thinking we're getting a 2. That's going to be a critical point. Now the big question, where is this derivative undefined? Well, if you have 4x minus 8, really it is a fraction, it's all over 1, right? And will this derivative ever be undefined? Well, I don't think that denominator is ever going to be 0. It doesn't say 1x, it just says 1. 1 is never going to equal 0. So I don't have to worry about it equaling 0 down there. I don't have to worry about it being undefined. Good. Sometimes that happens where you don't have to worry about 1. You got to try it, but a lot of times it's going to happen. So I have 3 critical points. Okay, so of all the bazillion points that I could have, we have narrowed this down to 3. So our maximums and minimums are going to occur from this list. Now we just have to figure it out. Okay, would you please take a moment, grab your calculator if you need to, I guess, go throw those numbers in, get the y values, and from there figure out what's your maximum value and figure out your minimum value. Okay, so pause and then go check me. Okay, you paused, right? So I'm putting -1 into my function. Let's see, 2 times -1 squared minus 8 times -1 minus 9. Okay, so check me here, right? 2 plus 8 minus 9. 10 minus 9. I'm getting a y value of 1. -1, if I put in -1, I get 1. Let's try 4. Putting 4 into my function. 2 times 4 squared minus 8 times 4 minus 9. Okay, 16 times 2 is 32 minus 32 minus 9. I'm getting -9. And the 2. I'll put 2 into the function to get the y value. 2 times 2 squared minus 8 times 2 minus 9. Okay, 2 times 2 squared is 4. 4 times 2 is 8. 8 minus 16 minus 9. Now I gotta think, because I got negatives. I'm trying to do this in front of you, right? 8 minus 16, -8 minus 9. I'm getting -17. I think I'm right, but okay. I cheated. I worked them out earlier, so now I gotta go check my answers. Okay, yeah, I think I'm good. Okay, so of all of these numbers, I'm checking my y values. So what's the highest y value we have? What is our biggest y value? Well, it's not very big, but it's the only positive one we have. So I think we have a maximum here at 1. Where do we have a minimum? The lowest y value that we have, -17. Now, does that mean that this -9 is not important? No. Now something else will happen there, but that's okay. What we're looking for is a list, hopefully a fairly small list, and from that small list, we can figure out maximums and minimums. We just don't want to try to test every single solitary point. We've narrowed it down to 3. Did you do okay? Let's try another one. All right. So now it looks a little more difficult, just a little, not much. Find the critical points of y equals, and it says x over x squared plus 1. Okay? So y equals x over x squared plus 1. You know me, I'm very concerned about endpoints, so go look on here. Do you have any endpoints? There are no endpoints on here. No, there are no endpoints. So quite frankly, technically, we really shouldn't even be doing this problem because extreme value theorem says it's got to be it's got to be on a closed interval. I'm going to go ahead and ask you to do it anyway, just to practice, but I know when I write my critical points down, I have no endpoints right now. Okay, so there's no endpoints. Let's go look for the derivative, and let's let the derivative figure out where it equals 0 and where the derivative is undefined. Okay, I think I might need a dark color on this one. Okay, looking for my derivative. What in the world are we going to do with this derivative? I'm thinking it's a quotient rule. You think so too? Okay, so my derivative is low d high, and the d high is 1, so I'm not really writing times 1, but I know there's a 1 there. Low d high minus high, and d low is 2x over the square of whatever's below. Okay, so far so good? Well, if we got to figure this out, let's clean it up a little bit. X squared plus 1, and I'm going to minus 2x squared. Well, what's an x squared minus 2x squared? Negative x squared plus 1, and I am over x squared plus 1, all quantity squared. I think that's about as good as I can make it. I can't cancel out anything, numerator, denominator, they're not really alike, so this is as good as I can make it. All right, let's take one at a time. Where would this derivative equal 0? If it equals 0, that means you have a 0 numerator. Let's go make your numerator equal to 0. Okay, so I'm taking my numerator and I'm letting my numerator equal 0. I'll do it over here. Negative x squared plus 1 equals 0. Moving my x squared to the other side and square rooting. And if you say 1, you are partly right. What else do you need? Plus or minus. That just gave me 2 critical points, a positive 1 and a negative 1. Both of those will let the numerator equal 0. Now we've got to figure out where the derivative is undefined. Let's let the denominator equal 0. Okay, so letting the denominator equal 0, x squared plus 1 all squared is going to equal 0. Well, I've got to square root both sides just to get rid of that quantity squared. X squared plus 1, well, 0 square rooted is still 0. Okay, so that means x squared is negative 1. And I hope you can kind of tell what's happening here. If you go square root, you're going to get square root of negative 1, and that's I, the imaginary number. We don't bother with those, so we say, yeah, don't even bother with it. Okay, I didn't have endpoints. Nothing is making the denominator equal 0, no real number anyway. But it is, the numerator is 0. I can make my derivative equal to 0. I have 2 critical points. I have a 1 and I have a negative 1. So we need to go test those 2 points. So my critical points right now are just 1 and negative 1. Okay, so critical points we have found are 1 and negative 1. Okay, so how do we figure out maximums and minimums? Let's go throw it back into our original problem. Okay, so how about this? Why don't you pause, go put the 1 and negative 1 in, check my answer. Seriously, pause and then go check, okay? Go. Okay, if I put 1 into my function, let's see, that's 1 over 1 squared plus 1. I'm getting 1/2. Did you guys get a half? If I put in a negative 1, x is negative 1, I have negative 1 squared plus 1. So I have negative 1/2. Well, I have a half and a negative half. I think I found my maximum and I think I found my minimum. And it says find the critical points. Well, these are our critical points. And I know that at 1, I have a 1/2, so there is my maximum. I'm going to go write max right there. And at negative 1, I have a minimum of negative 1/2. So I have maximum minimum values and I have the points. So whichever way they ask me, I'm fine. Hopefully that wasn't too bad. Okay. Let's keep going. Let's give you a slightly different kind of problem, but hopefully you're getting this idea of of your critical points and how you figure out your maximums and minimums. Takes a little bit of time, but hopefully not the worst thing you've ever done. And we're getting close. Okay, I can almost hear the groans because, oh my gosh, we have a square root and we have an x. It's going to take a little bit longer, I think, to get this this derivative. So let's go figure out the derivative and let's go do it. Let's just get it all done, right? Okay. Again, if I'm thinking of maximum and minimums, I've got to get my critical points. Critical points, endpoints, where derivative is 0, where the derivative is undefined. Technically on this one, it's not giving me endpoints, although there are actually endpoints, believe it or not. If you take a look on there, there's really only a few numbers that x can be because you don't want a negative underneath your radical. There's kind of built-in endpoints here because you have 4 minus something squared. Your radical can be a 0, but you don't want your radical to be a negative number, and it's very possible if you put in a number like 3 that you're going to have 4 minus 3 squared, and that's going to be a negative under the radical. So there's actually kind of built-in endpoints here of a 2 and a negative 2. Just throwing that one out there. Okay, but I'm not even worried about that right now. Let's go ahead and get our derivative, and then we can figure out what happens with this derivative and figuring out if it equals 0 and where it's undefined. Okay, so what in the world are we going to do with this derivative? Ew, besides panic. Let's call that a half power. Okay, so I've called the square root a half power. Maybe that will help with the falling boxes. And you have to realize this is also a product rule, right? Okay, so no joke. I'm going to step out. I'd like you to really, no joke, pause it. Just go get your derivative and stop and check your derivative with somebody else and check your derivative with me. So pause, get a derivative. Okay, go. Okay, I'm telling you this derivative is not going to be pretty, and it's going to be better only if we do something to it. So you're paying attention, all right? Okay, let's go get our derivative. Probably needing more space, right? We have a product rule, so I've got to do keep it, change it, keep it. Okay, I'm keeping x, and I'm changing this quantity to its derivative. So it's a chain rule. Drop down the half. Keep the 4 minus x squared, and now what does the half drop down to be? It has to drop by 1, so that becomes negative 1/2. Are you finished with this derivative? Nope, you took care of the outside, now you need the inside. Chain rule says derivative of the inside. What's the derivative of this inside? Negative 2x. Okay, it's ugly, it will get better. Just keep going. Okay, kept it, changed it. Plus, I'm keeping the ugly part, the 4 minus x squared all to the half power, and then at least the derivative of x is 1. Okay, let's clean it up. Let's make it look better. I promise it gets better. It doesn't get great, but it gets better. Okay, let's see. If I start putting things in different places, right, like making a fraction out of it, I see there's my half. So I just took care of the half, and while I'm here, I'm going to go put the x up at in the numerator. I'll clean that up in a minute. So there's my x and my half. I have 4 minus x squared, which is to a negative half power, so that goes down in the denominator. I'm going to write it as a square root. And I have a negative 2x up in the numerator. A negative, what? Oops. Yeah, we'll write it, a negative and a 2x. Well, I'm thinking I can make that look a little better. Do you see what you can do here? I've got a 2x squared and a 2 down here, so I think I'll just go make that look a little nicer. I think I can cancel out my 2's and just call that negative x squared. So I'm just going to go make that say negative x squared. Maybe. Okay, that's just the first part. And to that, I am going to add a 4 minus x squared, which is being square rooted. And I wrote it like a fraction. Okay, here's the deal. If you're going to figure out where this derivative equals 0 and where this derivative is undefined, you've got to have this as all one fraction. And what do you need when you add fractions? You need a common denominator. And I know, I can hear the groans, I can hear the whining, but actually, this is going to be better than you think. So, first of all, think about what's your common denominator? It's that radical, right? Okay, so I'm going to leave the first one alone. Negative x squared, and I have radical 4 minus x squared in the denominator. What do you multiply the second fraction by? Square root of 4 minus x squared over square root of 4 minus x squared. Now you see why this is actually going to be okay? Okay, so if I multiply these two together, well, my denominator is square root of 4 minus x squared. What happens to your numerator? Square roots cancel. So you have 4 minus x squared. Now you can put this all together as one big ugly fraction. That's okay. You know the denominator is square root of 4 minus x squared, your common denominator. Negative x squared plus another negative x squared is negative 2x squared, so I have 4 minus 2x squared. Whew. Okay, derivative is done. I think I've done that before. Okay, let's now figure out what would make your numerator equal 0. That's what makes your derivative equal 0, and what would make your derivative undefined. So we're setting numerator equal to 0, denominator equal to 0. Okay, so setting my numerator equal to 0, right? Let's do that over here. 4 minus 2x squared equals 0. So 4 is 2x squared. I'm dividing by 2. So I'm getting x is positive or negative radical 2. Not my favorite critical point, but it's better than others. Okay? Now we'll go think of what makes the denominator equal 0. Oops, that's supposed to be a different color. Okay, so what would make that denominator equal 0? If I come over here. Square root of 4 minus x squared equals 0. Maybe you can do this one off the top of your head. If you can't, square both sides. Put the x squared on the other side. And what do you think? Square root of 4? I'm getting a positive or negative 2. Okay, we now have 4 critical points. And quite frankly, that's a lot of critical points. It's kind of unusual. So let's go get these 4 critical points and we'll figure out what values we have and we'll be okay. All right, so I've got my little handy dandy cheat sheet right here. You can check me, I promise here. It's actually all right. If I go put in, first of all, I'm going to go check the 2. So let's just go even think about what happens with 2. I have 2 times the square root of 4 minus 2 squared. Well, that makes a 0, and 0 times 2 is 0. That wasn't so bad. What about negative 2? Negative 2, 4 minus negative 2 squared is still 4. I'm still getting a 0. Okay, both of them gave me zeros. What about square root of 2? Well, x is the square root of 2, and now I'm taking square root of 4 minus square root of 2 squared. So I'm getting square root of 2 times a square root of 2. And what's square root of 2 times square root of 2? 2. Oh, well that wasn't that bad. Let's try the negative radical 2, right? So it says x, so you have negative radical 2, and you have square root of 4 minus, and let's see, if you square root a negative radical 2, a negative times a negative is a positive, so we're still getting that 2 thing again. So I have a negative radical 2 times a radical 2, I'm getting a negative 2. So all of these ugly numbers, my y values are 0 and 2 and negative 2. I think we have just found our maximum and we have just found our minimum. So here's our minimum, here's our maximum. Oh, that took a lot of paper. Yuck. Okay. Almost done. Almost done. Okay, let's go find our extrema, and it says 1 over radical 9 minus x squared. So let's go try to figure this out. Again, no endpoints for the moment. Let's go figure out this derivative. We'll figure out where the derivative is 0. We'll figure out where the derivative is undefined. I would recommend that you rewrite this as 9 minus x squared all to the negative half power. Now, if you don't mind, pause video, please. Get this derivative, and then check, and then go on. So pause and get the derivative, okay? Go.